Welcome everyone. My name is David Talby. I'm the CEO at Johnson Labs, and with me today is Veysel Kokaman, who is our CTO. And our goal today is to share with you some recent benchmarks comparing current frontier LLM on different sets of tasks related to understanding clinical and biomedical text. We're going to do a short overview of the different models and APIs that we'll compare. Then we'll basically break this into two parts. I'll present results on blind evaluation by medical doctors on comparing different medical LLMs directly on tasks like question answering, clinical information extraction, and clinical text summarization. And then Veysel will talk about new benchmarks that compare both LLMs and clinical NLP APIs on tasks like name entity recognition, assertion status detection, de-identification, and clinical coding. So let's begin. We are going to be comparing here 5 commercial LLMs and NLP providers. On the LLM front, really for the most recent benchmark, we picked what is considered to be the strongest commercial frontier LLMs out there. So from OpenAI, it's GPT 4.5. So that's the newest still in preview model from OpenAI, which is considered kind of really the highest end model at this point. And since we wanted to compare on things like accuracy, relevance, factuality, we wanted to compare against really the top performing model from OpenAI out there. The second LLM we compare with is Claude from Anthropic, where right now the kind of frontier and most used model is Claude 3.7 Sonnet. So that's the one we compared with. In terms of commercial healthcare specific APIs, you'll see comparisons versus the 3 big cloud providers. So from AWS, Amazon Comprehend Medical, for Microsoft Azure, Text Analytics for Health, which is also it's a healthcare specific service for Microsoft, and from Google, the Google Cloud Healthcare Natural Language API. We'll be comparing them to Johnson Labs medical large language models. Johnson Labs offers a suite of healthcare specific LLMs for different sizes, all the way from 7, 10, 14 billion parameters to, as you can see, 24, and then going upwards to high double digits and low triple digit sizes. The two most commonly used ones are what we call medical LLM small and medical LLM medium. We've already shown before benchmarks to do this kind of blind evaluation comparisons on medical LLM small. What you'll see today are newer benchmarks that compare medical LLM medium. So everything you'll see today relates to our medium medical LLM. When people consider Johnson Labs models, the main 3 reasons that people focus on are the ones listed here. First of all, Johnson Labs' one and only promise and mission to the healthcare community, the life science community, is that we will keep you the state of the art for healthcare specific tasks. So as you'll see today, really all we do every day is look at any new LLM, any new paper, any new data sets, any new idea or trick that someone claims. If it works, if it generalizes, if it reproduces, our job is to give it to you in a production grade manner and do it fairly quickly. We've been releasing software and models every 2 weeks for over 8 years now, really to keep the entire community with the state of the art. The second thing about our models is that basically we do nothing as a service. All our models run privately within your infrastructure, meaning that we'll give you the LLMs. So if it's on-premise, we'll give you a Docker container with an OpenAI compatible API. If you're running, for example, on Amazon Bedrock Marketplace, you'll have a Bedrock or SageMaker compatible API. But the point is, everything will run within your infrastructure, within your VPC. You never send your data to us. You never send your data to any other third party. And in fact, these LLMs can work within an air-gap environment. So this is designed for high compliance deployments in healthcare and life science. The third interesting thing about our models is that we are the only one from the selection you'll see here who do not charge per token. We charge per server per year. And this pricing model is really designed for basically for scalable deployments. So of course, yes, if you need 1 or 2 pages, it's much cheaper to do it with an API. You'll pay maybe under $1. But if you're looking to analyze maybe 50,000 patients, 100,000 patients, 5 million patients, 10 million patients, you'll really run into high 8 figures when you look at some of those commercial APIs, where Johnson Labs would enable you basically to scale on a much lower budget. All the price with Johnson Labs, basically you have 2 costs. You have the licensing cost of the model, and you have the hardware cost because you host the model yourself. But in all the cost comparisons you'll see here, we combine both. So we combine what it would cost, for example, to call OpenAI versus what it would cost hardware plus licensing to call Johnson Labs, so that it's a fair comparison. In general, in healthcare, there's been quite a lot of work, mostly academic work, over the past 2-3 years on how to evaluate large language models. And there's broad agreement that you need to evaluate across multiple dimensions. You want to look at clinical accuracy, you want to look at relevance, you want to look at completeness, you want to look at safety, you want to look at just clarity and writing style, you want to look at hallucinations. Here's one of the papers we recommend if you're just completely not familiar with this space. But in general, at Johnson Labs, we do the same. We evaluate our models by clinicians across multiple dimensions. You'll see a subset of them today. And we also have an alignment process to look at different kind of safety issues. Here's an example of why you'd really want to evaluate things before you send them to production. Clinical note summarization is a popular use case for LLMs, and it's a good one because in many real-world cases, LLMs can summarize clinical notes and clinical records basically as well as human experts. And there's been several now kind of blind evaluations, human versus AI, that have shown that often humans prefer AI-generated summaries, and also that AI-generated summaries often hallucinate less than humans, surprisingly so, but that is the case. However, it still doesn't mean that it would actually help you in practice. This is one study from University of California, San Diego, that showed that primary care physicians who use ChatGPT to respond to patient messages actually spend more time on the tasks, because what they had to do, instead of reading the question and answering, they had to read the question, look at the draft, think about the draft, edit it, and then hit send. So it actually ended up taking them more time. One of the known issues is hallucinations, and LLMs, as we know, do hallucinate sometimes. And when they do it in a fairly convincing manner. So you really need to be on your toes to understand and catch what they do. It also means that you need some process to review and clean those hallucinations, which can be, on one hand, they can be fairly small in terms of the task, but also fairly important. You can see one example, you can see changes in symptoms. You can see changes in medications that have been ordered, which could really cause harm to a person. So one of the things you need to do is really you need to be superbly careful on just the factuality of the answers you have there. So these are one of the things we test. In general, why you'd really want to test things before you go to production, so that your users don't end up spending more time because you deploy the tool. Within Johnson Labs, for example, one of the things we actually built a hallucination detection tool specifically for LLM-generated medical content, and that's one of the things we use to test and improve our own models. So what we're going to go through now are results from a process of blind evaluation of across models by practicing medical doctors. And here's a bit about the methodology. We generated more than 200 questions in 4 categories from scratch. It was important to us that these are brand new questions to eliminate any chance of data contamination. Okay, so we know that none of the models and none of the APIs here have seen those questions before, which happens very often if you use academic benchmarks. We tested this on 4 kinds of tasks: medical text summarization. Here's a radiology report, please summarize it, right? Here's a discharge note, why was this patient here? Clinical information extraction. Given this pathology report, what is the tumor staging, for example, right? What drugs do we prescribe? Biomedical research, which means here's a PubMed abstract. was this trial successful, right? Was this medication, was the medication given better than the control arm? Okay, so those type of questions over a biomedical text. And the last one is open-ended medical knowledge. So, without any context, right? What are the common causes of, the flu, for example? Just to look at kind of general medical knowledge. So these were the 4 tasks, and we had a set of questions in each of those tasks separately. The team that did the evaluation is the 4 people listed here. We initially started with a slightly larger group, but those are the people who did well, not only on the clinical knowledge, but also in terms of inter-annotator agreement and consistency over time. So here's how this works, the random line evaluation. We, for example, if we have a clinical text summarization task, we take, here's the original visit summary. We send it to 2 LLMs using the standard API. We get the response back, and then we show this to the medical doctors, 2 people each on each evaluation, and we say, here's the original, here's model 1, here's model 2. We don't tell you which is which. We randomize the order. And then what we ask you to do is we ask you to tell us which one you prefer. And you can say, I prefer model 1, I prefer model 2, or they're both the same to me. On top of that, we have done work to evaluate inter-annotator agreement, right, to make sure that people actually agree with one another, right, and the results are not kind of randomized or the preference of a single person. We've also done washout period analysis, which is basically means asking the same people the same questions, but 2 weeks apart, basically to see if people change their mind, right? So it's important to see that when someone says, yes, I really prefer this over this, that they're actually stable and consistent, and it's not just kind of a, based on the current mood, right? Or really kind of it's a small preference either way that could change. So we want to see the results are meaningful and stable. If you we'll talk about a bit more about where you can find more details on this. When we ask people which model you prefer, we don't just ask it this way. It's a bit more structured than that. We ask them to decide which one they prefer on 3 separate dimensions. And we put in quite a lot of work to define the dimensions and make sure we have high understanding, high agreement across annotators on what each dimension means. The 3 dimensions we ask the doctors to evaluate this on are factuality. So basically, is the answer factual? Okay, so for example, if I asked you to extract, for example, which medications, right, were prescribed, look at it and say, okay, look at it and say, is this actually the correct answer? If you did summarization, is the summary conform to the original? The second dimension was clinical relevance. Okay, so basically, is the result clinically relevant? Okay, for example, if I look at the summary, we took a 2-page discharge summary, we summarized it to 1 paragraph. Does this include everything you think you as a doctor think is critical to include in a summary, basically, right? So all the clinically relevant fact there. And the third dimension we looked at was conciseness. Basically, how short and how clear is the answer? Do we like the writing style? Is it straightforward? Does it get to the point? In the evaluation we'll show you today, we haven't really, we will not show conciseness, because conciseness can be controlled to an extent via prompting. So we'll, in the evaluations we'll show you, we'll focus on comparing factuality and clinical relevance. If you want to get more details, for example, what prompts did we actually use for each of the LLMs? Because we did some prompting work for everything we compared with. What are the actual questions? How did we calculate inter-annotator agreement? All the gory details, which are obviously important if you're looking to reproduce this or understand more about what and why we did. This is now, we have submitted those as paper with all those details under peer review. And once they pass the peer review stage, we'll make them public, hopefully soon later this year. And without further ado, let's look at some of the results. This first chart shows the comparison between Johnson Labs medical LLM medium and OpenAI's GPT 4.5 on the entire dataset. So all 4 tasks that I described. And here's what you can see. If you look, for example, at factuality, you'll see that in 69% of the cases, basically the evaluator said, look, this is the same, I have no preference. But when they do have a preference, 18% of the time they prefer the Johnson Labs model, and 13% of the time they prefer GPT 4.5. If you look at clinical relevance, you can see that about half the time the evaluator said, look, the models are the same. When they have a preference, it was 29% of the time prefer Johnson Labs, 26% of the time they prefer GPT 4.5. So as you can see here, in general, the Johnson Lab model has a slight preference. What is important though, the Johnson Labs model costs 1/100th of the cost of GPT 4.5 to run this kind of test. Okay, so not only do you get higher factuality and higher relevance, you get this at a far, far, far cheaper cost. And as I mentioned before, this includes both the hardware, the hosting, as well as the licensing costs from the Johnson Lab side. Comparing to Anthropic, to Claude Sonnet, so first of all, Claude Sonnet is a much more is a far cheaper model. So here, running the same benchmarks, all questions on Claude Sonnet 3.7 cost 5 times more than what it costs to run this on the Johnson Labs medical LLM medium. But still, even though it was 5 times more expensive, as you can see, Johnson Labs is heavily favored here on factuality and also slightly favored on clinical relevance in terms of all those tasks and all those questions. Going more specifically, let's look task by task. Probably the most popular task that we see nowadays is clinical information extraction, which means, for example, here's the radiology reports, please extract kind of the key findings, the key measurements. Right, here is an intake note for a patient, please extract social determinants, right, or patient history or allergies. So basically, having specific questions, for example, given the note, what procedures did the patient undergo? Did anlotinib benefit the patient? Right, so basically very specific facts that we want to extract from a clinical text. And this is useful whether you're looking to build risk prediction models, doing population health, doing real-world data, real-world evidence, looking for patient safety events, or even building risk models that depend on information from unstructured data. As you can see here, versus GPT 4.5, you can see the preference numbers on factuality. About 2/3 of the time, 68% of the time, the models are equal. But when they are not equal, the Johnson Labs model is preferred 3 times more often than GPT 4.5 in factuality. Okay, so for example, if it's important for you the model does not hallucinate and returns things that are actually grounded in the facts and the contents that you give it, then the Johnson Labs model is heavily kind of tuned and aligned and designed and trained to do exactly that. On clinical relevance, also you can see that there's almost kind of more than 50% more often the Johnson Labs model is preferred. So about half the times the models are equal, but when they are not, Johnson Labs model is preferred 29% of the time versus 18% of the time where GPT 4.5 is preferred. On clinical information extraction, here's the comparison versus Claude Sonnet 3.7. So what you can see here is, first of all, the models are equal more often. So 74% of the time on factuality, 71% of the time on clinical relevance, the models are essentially the same or have the same level of preference. But when they are not, Johnson Labs model preferred 4 times more often than Claude on factuality. Okay, so Claude seems to still suffer from some issues around factuality and hallucinations that the Johnson Labs model, at least the current medical LLM medium, does not seem to have or seems to have less of. The second specific task that we'll want to show results on is biomedical Q&A. So here the goal is to look at a PubMed abstract, clinical trial results, regulatory submission, and answer specific questions. For example, you see some of the sample questions here at the bottom of the slides. Given this report, what biomarkers are commonly negative in APL cases? Given the article, what is SNFL used for? Right, so really this kind of read the article, understand what's going on, give me a summary, or just really basically answer a specific question, so that as the human I don't have to go and read the article. And you can see some of the results here. Versus GPT 4.5, Johnson Labs is preferred 2.5 times more often on clinical relevance. As you can see, it is preferred more often on factuality. So on factuality, 72% of the time, the models are similarly preferred. But when there's a difference, the Johnson Labs model kind of wins more often, right? 18 to 10. But when you look at clinical relevance, which is really usually what you care about when you look at this kind of question answering, right? Is the short answer you give me actually the most clinically relevant, right, based on this context, right? So kind of, do you give me everything I need to do in an answer to really understand what I need as the clinicians judged it. So you can see about half the times the models are equal, but when they're not, the Johnson Labs models was preferred 38% of the time versus only 15% of the time for GPT 4.5. One of the reasons could be the fact that the OpenAI models are more geared towards kind of the general public. So, laymen, basically patients, versus what we did here was looked at what medical professionals would be interested in seeing. So this is at least these are the people who are judging, right, this specific benchmark. When you compare versus Claude Sonnet 3.7, what you'll see here on biomedical Q&A, the models are very similar on clinical relevance. So about half the time, there's no preference, but when there is a preference, Johnson Labs is preferred 25% of the time versus 22% of the time for Claude. But here there is a big difference on factuality, right? So 2/3 of the time the models are similar, but when they are not, the Johnson Labs model is preferred 2.3 times more often than Claude on just returning factual results, meaning that the medical answer I give you actually is based, right, on the context or report or article that was there. So those are just some of the metrics we want to share with you there. As I said, the peer-reviewed papers will be out hopefully within the next few weeks once we reform the kind of really form the peer review process and go through that. And with that, what I'd like to do now is transition over to Vaisal, who will share benchmarks on different types of tasks. As I said, clinical coding, the identification, entity recognition here, assertion status detection, that are more specific tasks, but also extremely common in practice. And you'll see comparisons here, not just to the LLMs, but also to some of the cloud APIs. And with that, Vaisal, over to you.
Okay, thank you, David. This is Vaisal, CTO of Johnson Labs. Now, on my part of this webinar, so I'm going to go over the more granular task, starting from name identity recognition, which is the pillar of NLP in medical domain, actually. So in this session, I'm going to go over name identity recognition, assertion status, the identifications, medical coding, and then compare them across different large commercial LLMs as well as cloud providers like AWS, Azure, and Google. So let's start with the name identity recognition. As you may know, Johnson Labs has its own library called Healthcare NLP, and then it has more than 2,500 different pre-trained models over there for different purposes, which I'm not able to cover all of them today. But for the name identity recognition, we have more than 130 different NER models that can extract 400 plus different medical entities out of the box, and they are really cheap and small models that you can't even club them together in one single machine, which means that you can even use 50 different name identity recognition models on one single machine without getting any memory error or any computational limitation. So on this part, I'm going to go over the Google Cloud, Azure Healthcare, and AWS Medical Component, which are the main healthcare APIs that you just send your data and then get your results without changing anything, which means that they are black box. You just send your prompt. Yeah, actually, it's not a prompt. You just upload your text, because these are all classic NLP out there. So they have millions of users, of course, just like we have thousands of users. So, but the key difference is that they return only a handful of entities from each category, which means that in Google Cloud Healthcare API, there is only one problem entities, which indicates all the conditions and symptoms and allergens, etc. On AWS Medical Component and Azure, they have 3 different entities that would correspond to problem entities. But on Johnson Labs, on our end, we have more than 20 different entities just to define problem and condition entities in more granular terms. For example, you may be interested in some disease, but what if you are interested, you want to differentiate between heart disease and findings versus kidney disease versus diabetes, right? So if you want one single entity still, you can still merge them within our pipeline. And if you don't like the results, you can plug out one of them and then plug in another one, or turn on and off different entities via blacklisting and whitelisting. So we offer all these options, while the other cloud providers only offer a handful entities for each category. Problem, like a problem category, procedure, drug, anatomy, severity, etc. Right? So just for tests, for example, we return more than 10 different granular results, while they are returning only 1 or 2 entities. And as I said before, if you want to change the behavior of this pipeline, if you want to rename it, if you are not happy and then use your own model within the same pipeline, we allow this, while the other cloud providers are only black box that you need to send your data and then get a results, and then you need to work through that results that you have nothing to do from now on. As David said, nothing we provide runs on our end. Everything is shipped to your end. You just use it as if it's just another library, like pip install Johnson Labs, and then you will be able to use it with our license. So, as I said, we have more than 130 different NER models for different purposes. There is a reason that we have that many name identity recognition models, actually, because even the same entity name might differ from domain to domain, from physician to physician. So we work with the human physicians, right? So as an annotator to annotate our own in-house data sets. And then we always see that their agreement level differ based on the domain in which they have an expertise in. So that's why we have different models for different domains for different purposes, which you can get different results given how you build, how you modify your pipeline. Then we compare these name identity recognition models by picking 9 different main entities, and then try to see how well they do compared to cloud providers, as well as GPT 4.5 and Anthropic Sonnet 3.7, which are the latest and state-of-the-art commercial LLMs out there. They are still black box, just like cloud providers. On the LLM side, as you know, you prompt and then you prompt and pray. Actually, you try to get whatever you need, and then just for small tests like name identity recognition, which is the major to like for the last 7 years at Johnson Labs, for example, for me, working on many different projects so far. Extracting the key entities are still the main business use case that people still sometimes try to use LLM for this purpose as well. Of course, you can do this, but why would you do this if you can accomplish the same with this small and much performant models, right? So that's our main argument here. So we compared our models, one single pipeline, against all the cloud providers out there. And then, as you see, out of these 9 entities, Johnson Labs NER models, name identity recognition models, are doing way better than all the others, and then making 2 to 3 less error than the other competitors. And then the more closest one, if you see at this chart, is the Azure, as you see, when it comes to cloud providers. And then in terms of LLMs, they are already doing really worse compared to what we can achieve with the small models, but it's still head-to-head. Anthropic and GPT 4.5 are head-to-head when it comes to entity extraction, but Johnson Labs is already going above 95%, even 98% on some entities, which are really rare, right? Like an alcohol and tobacco consumption. So which would be really surprising to see that even GPT 4.5 is doing really worse when it comes to extract that granular entities over there. So the next one is assertion status detection. So it is a very popular use case, and then surprisingly, people still use rule-based negativity scope detection. In one sentence, what negative scope detection or assertion status is that it is trying to detect the context of the entity that is extracted by NER models, which means that the patient might have a diabetes, or the patient's father or mother might have a diabetes in the history section of the clinical note, right? So if you want to find the patients with these keywords or these named entities, and then try to invite them for a clinical trial, let's say, if you don't pay attention to assertion status, maybe the term is being used in a negative context, right? The patient denies pain, right? So there is no pain over there. Or the father with Alzheimer's. So the Alzheimer is not the patient doesn't have an Alzheimer, but the father has an Alzheimer. So this kind of negativity, this kind of status, like context status, is highly important to filter out some of the irrelevant cases for your downstream task. That's why assertion status detection have 5 to 8 different labels as a classification result, right? Like if it is there, it is present. If it is not there, like patient denies pain or no evidence of headache, etc., it is absent. Or mother with Alzheimer, it is associated with someone else. Or the patient have a short of breath, right, when climbing the chairs, like climbing the stairs, right? So these kind of conditional events also really important when you are trying to filter out certain patients given the entities. So that's why we annotated our own data as well as using the I2B2 data set because that's an academic benchmark that everyone else is using. We try to see how well we can do in this domain. And at Johnson Conway, we have 5 different means of doing this, not just using the keywords, because as I said, most of the healthcare institutions are still relying on like more than 20 years old regex-based negex context, like negativity scope detection. And they are mostly focusing more on the family, absent, and present status, 3 status. But here we focus more on like more than 6 to 9 different status label, including planned, past. Maybe the patient has a patient will need a head CT, so this is a planned activity in the future. Or patient had been using metformin for the last 2 years, right? Or had used metformin like 2 years ago, which means that this is a past event, which you shouldn't consider as of today. Anyway, so we have 5 different algorithms to do this. Their sizes differ, their performance differ, but we annotate our own data, and then we have a way of merging all of them for certain entities, which means that some of the algorithms might do well on certain entities, certain labels, while the others are doing decent on across all the labels, right? That's why we fine-tune even the LLM version of this, to see how far we can go and then beat the other solutions. We compared with GPT-4o, Azure AI, and AWS Medical Component, and we even published a paper on this, which you can go ahead and then read right now. I got a chance to present it in a conference last month in Italy. So these are the metrics I presented over there, and as you see, our combined pipeline is doing way better than the other commercial solutions out there, and then our fine-tuned LLM by itself can beat the rest of it. But as I said, it would be an overkill if you try to extract assertion status labels just with LLM. That's why we have the similar performant models, which are as small as like a few million parameters, not even a million parameters over there, that you can use and then accomplish whatever you want without using any LLM in the pipeline. And then the latest best, according to latest best scores on this data set, so we are proud to say that we are already doing way better than all the other approaches. And then you can go ahead and then combine all of this within the same pipeline without getting any memory error. So we also have pre-trained assertion detection models for certain verticals, certain domains. Let's say, for example, just for oncology, we have another assertion model. You can go ahead and then download and then start using it from our model hub. Just for smoking detection or menopause, right, which is very niche domain, which means that if you are working on that domain and then use a generic assertion detection model or oncology assertion detection model, you may not get the same result. You may not get the accurate results as you would get from that domain. That's why we have different pre-trained models fine-tuned with different data sets. With different algorithms, by the way. Whenever we ship one model, we train the same model with different algorithms as well, as I mentioned in the previous page, and then ship them. So you have 4 to 5 different versions of the same model, given your hardware requirements, like given your hardware on your system, so that you can go up or down without losing any accuracy. So the next task is name identity. Like when you get a name identities, the next task is you want to map this to certain medical terminologies, right? ICD-10, Sonnet, UMLS, RxNorm, Medra. These are all medical terminologies, and Johnson Controls already has terminology servers to accomplish all this in one single platform. It's a UI and API-based platform that you can ship into your on-prem. But we would like to see what is powering that terminology server here, and then how you can accomplish the same within your own pipeline. Which means that every component that I'm talking here can be connected to, can be clubbed together and then used in the one pipeline, so that the pipeline that you run on one single node can run over 1 billion node if you have enough cluster environment to run this pipeline without changing any code, which means that the same pipeline can scale over billion or millions of nodes without changing any single line of code if you have the right cluster setup. So in this task, we evaluated our capacity to extract RxNorm, because RxNorm is structured codes assigned to medication entities, like a drug, and then they like a brand name or ingredient, right? So we extract the entity set first, and then send it to the RxNorm resolver, and then see how well it is able to detect these codes. And there's no hierarchy between RxNorm codes, as you might see in ICD-10. So in the top 3 accuracy, healthcare NLP is right now 30% better than AWS Medical Comprehend, which means that because we don't only return one single result for one, because it might, like, given the context, the code might differ as well. It's happening especially in ICD-10 and HCC and Sonnet, by the way. So, but AWS Medical Comprehend, it is 56% accurate in the top 3, which means that 56% of the time it is returning whatever you need in the top 3. But we are returning 83% of the time. And then if you want to go deep dive and then change the behavior of this pipeline, you can always modify that pipeline, because we have more than 300 different Colab notebooks just to explain how you can modify your pipeline or use certain models over there. And then in terms of cost, because that's another concern, right, as David also mentioned. So healthcare NLP can cost less than 5,000 to be able to process 1 million records on your on-prem, while you need to pay more than $25,000 to process the same amount of data while sharing your data with AWS through API. Of course, they have private and enterprise versions as well, but it is still, you send your data, and then you should be okay with whatever return from that API. But in healthcare NLP, everything happens on your on-prem, and then as long as you have a license, you can do RxNorm, ICD-10, Sonnet at the same time, as well as the identification on as like after this task with the same license. So that's still the same license fee over there. And then GPT-4, I'm not even talking about GPT-4.5, which is 10 times expensive, by the way. It is $44,000 just to process the same amount of data, and then it's only able to find 10% of the RxNorm codes, which is completely useless. And we have a blog post about this. Please go ahead and check this blog post, how we evaluate, and you can reproduce the same on your own end, because we have the notebook as well mentioned in the blog post as well. So the last part of this webinar is clinical identification, which is the most popular use case of applying NLP on in a real world scenario, right? Because you usually, especially while you try to fine tune your own models or share your data with the other APIs, which is really common use case nowadays, right? Or you sell your data, let's say, you want to fine tune your own model via other companies, and you need to share your data with them, or you need to share the data with the other hospitals within your network. Over there, you need to identify according to HIPAA, GDPR, or some other regulations. You need to remove all the sensitive information, like protected health information, right? So the masking is, you need that first find the sensitive information, which is the identity recognition task. Then you need to mask them, which means that you remove them or mask them or the shade them so that no one can see it. But of course, if you want to keep the consistency, integrity of the document, you need to obfuscate them so that it is still the same useful text. Otherwise, if you have just mask, like this one, imagine all these all these red highlighted parts are just mask, which like black or empty or asterisks, right? This is useless if you want to use this data to fine tune another model or to train another model, right? So that's why we usually get a demand of, like we usually do obfuscation, which means that we replace each entity by keeping the integrity of the document with the fake entities. If it's female, we replace with the female names. If it is an address in the United States, we replace in another address in the United States. So the same zip code structure, same phone code, so that if you see the obfuscated note, you don't understand. The goal is you don't understand if it is okay. But ideally, you don't have, the goal is not to be able to find the target patient, but most of the time you don't even notice that it is an obfuscated clinical note. So we have a whole suite for this at Johnson & West, which you can not just the text data, you can also identify and obfuscate the structured data as well as medical imaging like DICOM, SPS, like some pathological slides as well. So, and then we have different different libraries and different tools for each one of them. And then we compare to other commercial solutions. We are happy to see that we have an end-to-end solutions for each one of them right now that can mask and obfuscate like more than 20 different sensitive information or the generic ones, which are usually 6 to 7. So we even have a live application that you can go ahead and then test right now, like did.johnsonwest.com. It is a live application. It can even detect languages out of 9 different languages. So it supports 9 different languages right now. You just type something on there, upload something, and then you will get the mask and obfuscated version right away. And then you have the notebooks to do the same on your own infra, of course, with the same model, because we are using the same model behind this API as well. This is only for the demo purposes, but you can test with your data as well. So we compare this with other cloud providers, as well as GPT 4.5 and Sonnet and GPT 4o, as we did with the other tests. And as you see, Johnson & West, the identification solution is between 93 to 98% F1 scores achieves. F1 scores, which is way better than all the other competitors over there. And then the most closest one is Azure. By the way, we don't even know what's powering these cloud-based APIs, right? So you just send your data, and then you should be okay with whatever you are getting. Even if it's secure, let's say you may not be able to modify the output. Maybe the address extraction performance or zip code extraction performance is not good, so you have nothing to do over there because you cannot modify it. But in this identification pipeline, you can just add one more line to your code, or we have notebooks to show how to do this. You can add one more model, or even add one more parameter to the existing model, and then you will achieve what you need, because it's very user-facing parameter interface over there. So, as you see, we are proud to say that we are making way less error than the other solutions out there when it comes to the identification. And then we also wrote a paper about this and then presented in a conference last month again. And then this is the comparison between our solution versus Azure versus Amazon. Like this is the cloud benchmark table. And then as you see on the binary, like PHI versus non-PHI, we are 96%. We are hitting 96%, while Azure 91 and AWS 83. And then the cost-wise, we are 6 times cheaper than Azure, and then again 6 to 7 times cheaper than AWS when it comes to the identification. Which means that if you process 1 million of records, this is what you are going to pay at the end of the day. And then when we do the same comparison with the state-of-the-art LLM solutions over there, like an API-based large language models, The popular one, GPT-4o, 4.5, and Claude 3.7, Sonnet. As you see, Johnson Labs is like hitting right now 96 again, because this is the same benchmarks, and GPT-4o is 80, like in 78, 79. 4.5 is 84, only adding 5% boost, and then Sonnet is 83, which means that they are around 80%, while we are hitting 96% on the binary PHI F1 score. And then our cost is again around $2,500, while GPT 4.5 is more than $280,000, which means that more than 100 times expensive than what we offer, with 12% more accurate, right? And then it's much faster and run on your on-prem, and then open box, and then way cheaper and easy to maintain. Okay, so I think we made the point here. When compared to cloud providers as well as the commercial LLMs out there, Johnson West, the identification solution, is doing stellar performance over there. Okay, thanks for joining the webinar. If you have a question, we'll be around, David and me, to be able to answer your questions. Feel free to ask your questions. We will be happy to answer. And then you can also connect us through other like LinkedIn or social media as well, so that we could be happy to share our experiences with you as well. Thank you.